Welcome everybody to the last press conference of today, and we have three speakers. The topic is novel carbon capture and storage technologies, and the speakers are Frank Schilling from Karlsruhe, Germany, Michael Kühn from Potsdam, Germany as well, and Juhlin from Finland.
Sweden.
You said Finland,
No, I said Sweden.
Okay, Sweden this time.
Don't accuse me of being Finnish.
Okay.
Maybe he's right.
On your holiday.
He is right.
Yes, I'm sure, yes. Okay, who's going to start?
We thought to make a short introduction about the concept, about the background, about the concept, and then we have in Germany a rather big project, the first European onshore storage site, which will be presented by Michael Kühn. He is head of CO2 Storage Center, the German one in Potsdam, and then Christopher Juhlin, who is specialist in geophysics, will present some of the new results in monitoring. Unfortunately, first it was planned to have the press conference tomorrow, then it would be parallel to the session where the absolute newest results will be in, so everybody is invited also to come to the session, I'm sure. And so I'll try to go through quite quick. So I put another question on, is geological CO2 storage safe? I guess that's one of the questions which is usually asked to scientists. If you look at the Earth from space, you see a lot during night, a lot of dots, light, and most is in the northern hemisphere. So light is nothing else than a special form of energy that's produced somehow in most of these countries by emitting CO2. There are different assumptions how the world energy demand will develop in the future. Most of these, or nearly all of them, say that within the next 20 to 50 years, coal, natural gas, and crude oil will play a significant role. All this, and this is one of the examples where one tries to reduce CO2 emissions by reducing the amount of coal, gas and oil. I would suggest that the next 50 years may be very important with respect to the emissions of CO2 into the atmosphere. We are all three non-specialists in climate research, so I only show some figures what happened during the last 1,000 years and what will happen in the next 50 years. So the CO2 emissions have gone up into the atmosphere, and due to the developing of different regions, especially China, India, South Africa and Brazil, the CO2 emissions probably will further increase. Our colleagues from climate research have put together a report, the IPCC report, and this is from the 2007 volume, and they rate it very likely to get, if we don't change our behavior, an increase in temperature between 3 and 5 degrees centigrade, something about that. As geoscientists, we do not only look into the future, we also look back. And if you look back several 10,000 years, you'll see there is a lot of flickering around. And there had been in the past, maybe 15,000 years ago, changes in temperature about 8 degrees centigrade within a few years. So what we are discussing here from my very personal point of view is not if life will survive an increase in CO2, an increase in temperature. The question is how many people will survive that. So it's also not a question if mankind will survive, it's only a question how many. I put this from the CO2 CRC project from Adelaide. We had 2 weeks ago a public presentation, and my colleague asked there, said every authorities reports that had appeared in the past 2 years has concluded that warming of climate system due to greenhouse gases increase is now unequivocal. And the question is, what do you believe? And from another great colleague, Amos Neer, he said, how do you want it? The crystal mumbo jumbo or a statistical probability? So you can use both. Both show we should change our behavior, and we want to discuss now about one of the possibilities. And I don't know anybody who says that's the golden bullet we have to save the climate, but it's maybe one of the options we have in a broader portfolio. And what we are up as scientists is looking, can we do it? How proper can it be done? Can we monitor it? Is it safe or not? And therefore we do some experiments all over the globe. And oh, that's wonderful. We'll get some music in now. So, first of all, why does everybody speak here German? No? Very good. Who has been flying in to Vienna? Me too. Came from Australia, so I was not swimming. Have you realized if you came in with a train from the airport, and for sure everybody comes in with a train because it's more environmentally friendly, on the right hand side you have a big refinery. They produce CO2, but all the oil you see there and the fuel they store in their storage area will be transformed to CO2 at the end. And every ton of this fuel will end up in about 3 tons of CO2. So, who is from Europe here? Where are you from? In United States, okay. That's even worse. So in Europe we have about 10 tons CO2 emissions per person and year. In the US it's a little bit higher, but there are some which are even better than the US. That's Australia. They came up with much more. But so we are talking about gigatons of CO2 every year. And if you would put a balloon filled with 100 liters of CO2 and then you bring it down into the underground at about 2 kilometer depth, 1.5, it ends up that you get the balloon will become much smaller. That's one of the reasons I said, let's put the CO2 down at least 1500 meters. It's also much more secure because then you can use the pore space more appropriately. So how should it be stored? So that's an example of a sandstone. So many people think the CO2 will be stored in a big cavern, but it won't be a cavern, it will be the pore space of a rock. So this pore space is usually filled with fluid, with water, with a saline brine, so it means a very salt-rich water, saturated water. And so that's not a drinking water, but the pore space full of it, and then you can pump in some CO2. But you won't get all the water out. So a lot of CO2 and some water will remain there. And at the end, if you stop injecting CO2, water will come back. But even if you would make a direct well to the surface, part of the CO2 will remain in the underground. It's the same effect you have if you want to produce oil or gas. You never get 100% out of the underground. Part will remain. And this behavior depends very strongly on the rock, and it depends on the wetting behavior. Then you have something which we call fluid trapping. You know this all from CO2 in bottles, in sparkling water.
It's the other one.
It's the other one, so that's still water. So sorry, that's this one here. And you have CO2 solved, and you can solve up to 6% of CO2 or 8% in this range in sparkling water. But if you increase the temperature or you go down into the interior, less CO2 will be solved in the water. And if you put in a lot of salt, then you can store even less CO2. So at the conditions we discuss for CO2 storage, you may solve 2 to 3% of the CO2 in water. As we use maximum 1% of the pore space, it will be still sufficient to solve everything, but it won't happen. But you can solve a lot of the CO2, and in nature already some of the CO2 is stored inside. And another trapping mechanism is that you simply use mineral reaction. You form carbonates. Most of them are exothermal, and so many people think, let's simply make chemical reactions and produce carbonates. The problem is that these reactions are usually slow, and this is one of the results of this CO2 here at the end in the reaction. Most silicate will form a surface covering, so in the long run the reaction will become slower and slower and slower. And therefore you would need more energy to make the carbonates in a technical process than you win for electricity. So this is not efficient. But in the underground this will happen. And then you have another form of trapping, that's the structure itself. So if you look at a dome-like structure, which we call anticlines, and if you have a low permeable rock above and a high permeable rock beneath, so you will trap it like in the sparkling water, still water here, here beneath the cap. So the idea is that when you start injecting, first you will have something like a cloud of CO2, and you need to trap it with a structure. If you wait longer, then more and more will be stored in the pore space. That's the residual CO2 trapping. And if you wait long enough, more and more will be solved in the water. And depending, and that's very important, it's not that every rock will react in a positive way. You can also have reaction in the opposite way, that you dissolve the rock. So you need the right rock composition. But if you do it in the right circumstances, you will also get the mineral trapping, the mineral reactions. And I guess for the first time it was done in Australia, and in the project Michael will present later on, there was done a risk assessment. And the risk is about looking at the cap rock, which means the low permeable rock. Is it tight? We have seen that there are faults inside. Maybe they are open so that CO2 may migrate outside. In Ketzin we have an old gas storage site. How does it interfere with the storage of CO2? What is the behavior of the faults themselves and the faults in the cap rock? What's with the safety of the well? Simply think, if you use this bottle and drill a well through, make a hole inside, it will become very complicated to get it dense enough so that the sparkling will stay in the bottle. So you may simply put in a hole. Today I'm a little bit brutal. Yes, so that's drilling. Yes? And now you have to tighten it again. And then we usually try to have several cap rocks so that we have a multi-barrier system. And then, last but not least, you need to understand the reservoir behavior. If you understand all these different regimes and how they interact, then you can think about the contamination of groundwater, the HSE above the surface, and what is also counted a risk, it does not really affect a person or a cow or the grass, but for the climate we have the risk that part of the CO2 may migrate again to the surface. Michael.
Yeah.
Now I have time to drink
So
my water.
after Frank showed to you now the principles of CO2 storage, and I would like to present to you or give you an idea of the project we are running in Germany, in Potsdam. It's a large European project of 18 partners from 9 European countries. But before I dive into it, I would like to say something about what Frank said before, the portfolio. The portfolio to mitigate the atmosphere, so to reduce the greenhouse gases in the atmosphere. CCS, carbon capture and storage, is just one way, one part of this large portfolio we are dealing with, and I would like to invite you as well to the sessions of the division Energy, Resources and the Environment. So this division deals with the entire portfolio of which CCS or CO2 storage is one. So now, after having said that CCS is one part of the portfolio, we are now asked, we the researchers in Germany, in Europe, in the world, to test if the CO2 storage can be long-term and can be safe. And this is what this project is all about. So the project is running, as you can see from this map, close to Berlin. So this is 20 kilometers northwest of Potsdam, where the institute which is coordinating the German Research Center for Geosciences is located. So this is in principle what we are doing. So we have one injection well, which you can see where we inject the CO2. We are injecting underneath a cap rock in 650 meters depth. We have two other wells close by, 50 meters and 100 meters away from the injection well, and you see a lot of equipment installed in these boreholes, so we call it the smart casing. We have installed here a system with monitoring devices which is unique in the world, so it's the largest monitoring ever done within such a reservoir. And what we are doing with this kind of monitoring, Chris will go in detail after me to say something about the geophysical measurements done. Beside the geophysical measurements, we are doing geochemical measurements here as well, and we are also investigating the microbiology. So what you can see is that the project is running since 2004, so most of the time was used to set up this large experiment. The injection started last year in June, and the project is intended to run at least until next year. So the amount of CO2 we would like to inject here are maximum 60,000 tons. So if you have worked with the question of CO2 storage, so this is definitely not the amount to save the climate here, but this is not the focus of this project. The focus of this project is the monitoring. So we want to investigate if our monitoring techniques are satisfying already, if they are good enough to see what the CO2 is doing underground, and if not, and any way to improve these monitoring technologies, because if CO2 storage will come, these will be the key factor to investigate the whole process. What our final aim is, you can see with on the picture on the left hand side with a black background. What we want to do is a 4D tomography of the underground. So 3D in spatial dimensions and the time. So what what humankind is encountered with when you're going to the doctor. So the computer tomography, where you are able to look inside in 3D into the body. This is what we want to do here on a larger scale. We want really to see what the CO2 does underground and with time, to understand if we do know the processes well enough already, and if we are able to predict, because so you have heard about it, we need to store the CO2 at least for 100 years, better for 1,000 years, or even longer for 10,000 years to be climate relevant. So and this there is no way around to take or to use the numerical simulation programs we do have to extrapolate the safety and the long-term behavior of the CO2 underground. Having said that, we are developing new techniques. You can see here one of the new developments we have done. So this is called the gas membrane sensor, which is able to detect the CO2 in the gaseous phase as well as in the dissolved phase. What you can see here is to the left, to the bottom left, how it is deployed in the borehole and how the gas diffuses into this sensor. So from the sensor downhole it is transported by a gas stream to the surface, and there we can measure the CO2, and this device has been used to measure or to determine the CO2 arrival after a couple of days, which you can see here. So at the top you see how the CO2 arrives in one of our boreholes, and at the bottom underneath you see how krypton, a tracer we have injected before the CO2 or in front of the CO2, arrives a little bit earlier and is indicating how the transport underground is working. So what we need to do is the numerical simulation, and we can use this demonstration site here to check if our numerical simulation tools are good enough already. So we do take this area to calibrate and parameterize our simulation programs, and this can be seen here. So to the right hand side you can see how after 1 year supposedly CO2 has distributed underground, and to the left, as you can see here, we are starting initially, you have a pressure gradient and you have a thermal gradient underground before the injection started. When you do start the injection you can see how the pressure increases because we are pumping something into an area where you do have already water, so you need to push something away, and pushing something away does increase the pressure. And with the blue curve you can see how the dissolved CO2 arrives after a while within this borehole, and then in yellow following is the CO2 arrival within the boreholes. And the most important information here is that it was possible actually with the numerical tools to very well predict the behavior of the CO2 and the arrival of the CO2 here within this first borehole where we have seen the CO2 coming in. And I would like to lead over to Chris.
Do you want to sit here?
Maybe I just switch. So we use various methods of geophysics, firstly to locate suitable areas where we can inject CO2 or below the surface. We want to find rock which is porous, as Frank mentioned earlier, where we can inject sufficient amounts of CO2, and we want to find locations where you have these porous rocks below a tighter cap rock. The other reason we use geophysics is we want to, once the CO2 is being injected, we want to be able to trace it in the subsurface without having to drill numerous boreholes. So we send down sound waves into the subsurface, we measure electrical field, we can measure gravitational fields, various measurements on the surface to try to track the CO2 below the surface, and also to detect any leakage from the reservoir to the surface. As Frank said earlier, we don't want the CO2 going back up again. So this is an example from the Ketzin site outside Berlin, where we carried out 3D seismics, and we see various cuts, and you can see the different colors represent where you have different rock types. And this is another example from the seismic. This is various cuts through the 3D volume. We see faults coming down there, the vertical lines, and the black line furthest down. I don't have a pointer now, but the black line furthest down, that it's below this horizon where we want to, or where we are injecting the CO2 at the Ketzin site. We also see closer to the surface some higher, some more colored areas on the right-hand side where natural gas is still left from the time when the site was used as a storage site for natural gas. So what we have here at the Ketzin site, we have the blue here where gas was formed, gas was stored from before the year 2000 at about 250 to 400 meters depth. We have a clay-rich cap rock, which is the seal, and below that we have porous formations where the CO2 is being pumped at about 650 meters depth. I can add that above the blue rock here, we also have a cap rock, an impermeable layer which served as a seal for the former gas storage. Now, there's various measurements being done to monitor the CO2 as it's being injected. The ones that are most advanced now are probably the electrical measurements. And what one sees here is that the reservoir or the formation that the CO2 is being injected into, it's a complex formation. It's what we call heterogeneous or non-isotropic, and that is the CO2 as it's being injected. It's not spreading out equally in all directions. It is following preferential pathways. So these electrical measurements indicate in which direction the CO2 is moving. And this makes sense from a geological point of view because the formation that we're injecting into, it's a series of small channels where we have both rocks which are fairly impermeable, more clay within them, and then we have rocks which are more porous, where there's a lot more sand, so old riverbeds. And this results in that when we inject the CO2, it will go in preferential directions. We also see this on the seismic. This is a rather complicated figure, but it's an indication of where you have porous rocks and where you have less porous rocks. So the blue is can be interpreted as less porous rocks in the reservoir formation, while the more colors, the greens and the red are porous rocks, and this is where the CO2 is presumably migrating. And we will repeat our experiments later on this year and in next year to confirm this interpretation. So very briefly, we're doing a number of monitoring studies. We're using geophysics, where we measure electrical fields. We send sound waves into the earth. We're doing geochemical monitoring, which was described earlier by Michel here, and as well as temperature and biological monitoring. So we're using an array of methods to monitor the fate of the CO2 at the Ketzin site. Thank you.
Okay, thank you very much, Chris. Are there any questions from us?
I'm Liz Gallagher from Environmental Research Web. Can you comment from the results you found so far as to how long you think the carbon dioxide will stay down there and how safe it is?
General or for Ketzin?
Either. Both.
So the problem is that the underground is very heterogeneous, and for Ketzin we have done some worst case scenarios. So at the moment I don't think that anybody has enough statistical data to make real models. So as Michael said, we want to calibrate the models, and so that's a prerequisite to really get into this question. But I guess we can simply go back a few slides. So what we have done here is, or the colleagues have done that, they said, okay, there is a risk that CO2 comes up the well, but that you can handle, because that's there you know exactly where it is, and if it's starting to bubble out in the basement of the well, you may fix that. But what's up with a fault? So we have a good indication from the seismics that the fault is quite tight, is more or less impermeable. But for Ketzin, we could also do a model, or we simply did it, open the fault and put in some sand, so make it highly permeable. And this ended up, if you would subsequently pump in CO2, which we won't do because our cloud maybe will never reach the fault at all, but if it would reach there the fault, then after 50 years, 10% of the CO2 will reach the old gas storage site. So the old gas storage site is under-pressurized. But we could say, okay, let's think it's not under-pressurized, so make a real worst case out of it. Then we will take at least another 50 years to get 10% of the 10% into the groundwater level, which would be in 100 years 1%. And the groundwater flux is there as high that you most probably won't even be able to measure by changes in the pH value the CO2 there. So that's the risk assessment, or part of the risk assessment for Ketzin. And it's very important always to say these results are for one site, and you need to confirm this for every site. And Ketzin is about, as Michael said, to learn more about from the risk assessment to the monitoring technologies, simply to be able, what can we monitor? But there is still a minimum risk that more than 1% come out. But then people start thinking, then, okay, then in 200 years it will be 2%. And that's a little bit more complex, because you have all these trapping mechanisms which have different time constants. So most probably you won't get more than 10% out of it at all, even if you would like to have it. But that's something we still need to learn more about it. Sorry, that's so lang quatscht, Michael, wie immer.
I would like to add here that we have to look at the natural analogs as well. So we do know that gas reservoirs, or where we now produce natural gas from, they have been tied for millions of years, and we need to investigate if the sites, or the potential sites to store CO2 are equipped as well with cap rocks and the entire environment to hold the CO2 for very long. On the other hand, we have a lot of experience with gas storage. So most of the gas is stored underground. So we do have experience here for decades already. So the technology is at hand. We do have the technology to do it, the CO2 storage, and so this is what makes us confident to take the next step. So as I said before, it's a very small amount of CO2 we are storing in Ketzin, because it's not about the amount of CO2 to be stored in Ketzin, but it's about monitoring. So what we need to do now is to take the next step and to see if the industrial scale projects are working as well, and there is indication that they do work as well. As you might have heard from the Sleipner project offshore Norway, you can see that millions of tons can be stored there safely, at least for now the 10 years they are doing this project. So we are quite confident to take the next step. However, we don't know yet if this technology is so far that we really can do it worldwide on a very large scale.
If one would know that, one wouldn't make research.
Herr Kroker, freelancer from Germany. Why didn't you use geol gas storage? Why did you go further down under the second cap rock?
Because the further gas storage site is too shallow. So you, as Frank showed with the balloons on this one diagram, you can see that you do have a quite dense CO2 phase when you're going deeper. So the target depth is from 800 meters and deeper, because there you do have a very high density of the CO2, and this is why we went further down into this structure, and as well because we did not want to have any interference with regard to the monitoring we are doing with the old gas, which is partly still within the reservoir, because as Frank said, you will never get all the gas out again, and this is the same with leaking reservoirs as well. So it is not too easy to bring in the CO2 in such a reservoir, and you can't get it out faster than you get it in. So this is as well something for the secure side of the CO2 storage. But these are the main two reasons, I suppose. But Frank might have further reasons.
Yes, I think it's what Michael said. I just came back from Australia. There is a partner project, and they inject there in a gas-filled gas, and so they have problem to see nearly nothing, because if you replace CH4 by CO2 in the underground at 400 meter, it will be very hard for Chris to separate that in a quantitative manner. So for good science it's always better to separate things, but it was required to have such a storage site because you also need to take into account the legal aspects of getting an approval for a site, and so you need to know already a lot about the geology, etc., to make it secure. And so we have an additional safety corridor with this second cap rock, but the main reason is what Michael mentioned.
So this would be a prerequisite for future storage sites to go
deeper down,
such way down, because of the compression of the gas.
That was the reason why they closed Ketzin. It was not deep enough even for natural gas. For town gas it was fine, but the pressure in our pipelines in eastern Germany, or in Germany or in Europe in general, is higher than the 200 meter of the Ketzin site. So you would have, a booster would have been required for pumping it back again, and that's too cost intensive. Therefore they go into the depth for the natural gas storage as well, that the pressure is fine. That was the reason why they made this old site empty. And the real ones will be deeper, but if you are shallower, everything becomes cheaper. So that's an expensive experiment. But if you would go to 1600 meter to the 3D seismic, as Chris has shown, you don't spend $500,000 or $1 million, you would spend 10 millions to see it. If you want to drill 3 wells into 1600 meter depth, it does not simply double the price, it's more a quadratic way of doing it. So to become shallower makes it less expensive for testing the monitoring technologies, and the experiment has much more monitoring insight than a big one will ever have. And the idea is to learn which one are the most sensitive ones, which is the cheapest way to get the best observation about the cloud. And therefore if you are shallow it's cheaper. That's an advantage, but it was not the general reason.
No more questions, I suppose. Okay, thank you very much, Chris, Michael, and Frank. And